just to keep our time moving, and I'm skipping over the teams or the rows that doesn't have a title. We'll prioritize the teams who did fill in their presentation title first. But next one is CMS-agent.
Hi, everyone. This is our group from the CMS-agent automated quantum espresso workflow for computational computer science. That I'll move to the next slide. Just to introduce everyone to our problem. So we are expert in many very excited state with emphasis on exciton. And for those who are not familiar, if you shine light into like materials, it can create this highly excited particle called exciton, composed of an electron hole. For example, on the left, on the lower left-hand side, these are called a singlet fission. Basically, the way that solar cell work is that you create an exciton, and this exciton can split up into like lower energy particle, and you can use it as an energy storage or as like energy source, for example. And to compute all of this, the process is quite involved. You can see that we start with like DFT calculation to get the wave function of the electron in your system, and then we have to do to compute the dialectic matrix as well as all the quasi-particle energy. Then you compute how they scatter with each other, and then you construct the Hamiltonian for the exciton. So all these are quite involved. The workflow is long and complicated, which means that it benefits quite a lot from having AI agent. And it also requires massive computation, which means that it also requires the having AI agent would be able to leverage against all of these problems. And just to distinguish ourselves from previous presentation, I want to introduce the main bulk of the code that we're going to work with, which is Quantum Espresso. Quantum Espresso is a DFT code that optimized for scalability, meaning they can handle a larger system compared to other DFT code like PySCF, for example. And it has robust parallelization, as well as it can handle a system beyond the molecular system. It has a periodic system, for example. It's also really good with high throughput calculation. You can run them in HPC, and it can be pretty fast. However, using Quantum Espresso requires a deeper learning curve, meaning because the code itself is written in Fortran, and you need to access to HPC, and you need to put in all the physical parameters, which means that using AI agent can help you with this. And with that, I'm going to start talking about the general workflow for our group. Our plan initially was to go all the way to excited state beyond the DFT, but unfortunately, we could not finish all of those in time. So for now, I'm just going to talk about Quantum Espresso. Our group, the way that we handle AI agents, that we find the structure in material project database, and then we connect to remote server through SSH, and then we write the input file as well as the batch submission script, and we run the computational everything on the server, and then we have the AI agent analyze the output. And with that, we're gonna go through the demo. Oh yeah, sorry.
Thank you. So when Supavit talking about we do all this, it's actually the AI doing all of this for us. You can see here, as we emphasize that the learning curve for Quantum Espresso is more or harder because it requires at least the HPC submission of jobs. You have to be familiar with the input-output files. It's Fortran. So what we can do is assume it is a good day. You want to do a calculation for silicon oxide, and you want to know whether this is the metal or semiconductor. You can just ask the AI agent to search for this material for you. You can see we wrote this search interface where it can interface with the entire data set and get the structure for you. There are 1,000 structures with the same elements, so we just use first one for illustration. And then you can also plot structure, which I will show you later. So the next step is, as I mentioned, in order to use Quantum Espresso, you have to generate an input file which has like hundreds of lines with different parameters. If you don't want to learn about it, you can use our code to let AI to generate this input file for you. So again, we ask the AI to generate this file. It generates the file for you. And very importantly, after this, we try to submit the entire job into the HPC system instead of running it locally on my local computer. Because again, we are using parallel computation for this material. It's really heavy. And you can see, here it's loading some basic set like things. And here I'm trying to ask the AI to do everything on the HPC system set to run this computation. And after this, you will see that this computation input file will be generated. And I will ask AI to estimate the computational hours for this entire progress, the computational tasks. It will always generate the input file for you, and it will also submit the job for you. You can see here it's running a lot of SSH commands for you. And after all of this, it will give you a review and you approve it, and that will submit the job. And job will be here, as you can see. So everything in this folder, they are generated not by me, but by AI. They are all, for example, if you look at this input file, how about this one? Again, there are many, many lines with different meanings. If you don't want to learn about it, AI generates for you. And it also gives the output, which is this after the job is finished. And you can read all those parameters like the energy, like the Fermi surface out of it. But again, if you don't want to read the entire output file, you can ask the AI to analyze the result for you. For example, here you ask what's the Fermi surface, it will read the output file and give you the Fermi surface. And you can also ask the band gap, and basically you can ask the AI to provide you all the information in the output file. In the end, I will show you the structure. For a given element, there are many structures, and we also implement this feature to output those structures for you, so you can visualize what exactly are you calculating. This is the same structure as the zinc oxide. Again, what we are trying to do is we are trying to ask AI to automate this really hard, parallel, complex workflow for us. I think this file to show.
Okay, and lastly, I want to do a summary. Firstly, I want to emphasize that we are using Quantum Espresso, but our workflow is really software agnostic. That is to say, with this software, you just need to do some minor modifications. You can use our workflow to use any first principles calculation software you want, like VAST, OpenMX, Siesta, PySCF, anyone that you can think of. And I'll also talk about the potential use cases of AI agents like this. Firstly, for theorists. Of course, this reduces the burden and make theorists focus more on theory instead of the tedious computation. Secondly, for those material scientists, they may be interested in high throughput material screening. That is, they want to do first principles calculation on thousands or tens of thousands of structures, and this can help them with high throughput calculations. Thirdly, some experimentalists, they're not very familiar with theory or first principles calculation. But if they want a quick analysis after they do experiment on certain type of materials, they can use our AI agent to give themselves a quick results. So that's pretty much of our introduction. Thank you. About submitting to HPC, essentially in terms of the security.
Yeah, so the HPC that we are using, there's like a 20 hours long password that can generate once, and it lasts for 24 hours. So you can just to the server without having to log it back in again.
So you don't want to send your key to
yeah.
You can ask the AI to directly SSH to the HPC after you set the key.
Yeah.
Yes.
I was also for the input files. I remember there's those. I remember doing it those longs. Are they potentials or something? How much hallucination is hallucination a problem in all those lookup files? And because they're very specific to what you're looking at, right? So how much of a problem?
The very purpose of our coding is to write some specific tools that you just need to fill in the values for some keywords. You don't need to type the full name of a keyword. So we use this to avoid hallucination.
And to add to that as well, we can provide the folder to the pseudo potential. For example, you have to provide on your own, and also it usually asks before it run anything. It usually asks you to look at the output first before actually running.
So you mentioned that it can also work for other software. So let's say if I want to do another one, what do I need to set up?
The one like for other software, you the tools for SSH and the tools for structures, they're fixed. But of course you need to write a new set of tools for that software because it involves like writing the keywords in the input files. So that's basically the effort you need to switch to another software.
So just the input file you need.
Yes, the helper tools for input files.
Now you reading the plots and these things you also need to do that.
Reading the plots, they are more like dealing with text files with ASE. So they maybe it requires some effort, but most effort will be the input file.
Even the input file can be automatically generated by some Python packages. You just need to write up the entire
Just want to reiterate, you actually just answered my first question, which is, so the input file is not all generated directly from the LLM, right? You have a function or a tool in your MCP that generates most of the.
Yes, but there is an important distinction because these computations, they are really, it needs you to input some physical knowledge into it, like the keep-on sampling. Sometimes you want to use a large basis set, sometimes you want to use a smaller basis set. Those are not generated by the Python package, but you can ask the AI to generate those parameters for you. And that's exactly what we're doing.
Another question I have is for the Slurm file. I assume it needs some knowledge about like the config or networking of your clusters. So how is that? Part
Yes,
of it?
actually, the HPC system we're using is the one called Perlmutter in Berkeley lab. So they have an online documentation. So when we write dog strings, we say you can reference their online documentation to learn about some knowledge.
I see. So it's not a fixed tool from the MCP. It's like the LLM go read the documentation.
Yes,
You can
kind of.
use it for different HPC.